and tell us about classifying group actions on hyperbolic.
Thank you. I would like to thank the organizers for inviting me, and it's a great pleasure to give a talk here. So I'm going to give a talk with slides, not because I like slides. Those who know me probably know that I almost never give slide talks. I'm usually too lazy to prepare slides. But I had to give this talk at another, actually at two conferences where the blackboards were not available. So I prepared the slides, and now I feel like I have to utilize them. So, what's that?
Now you're too lazy not to use slides.
Yeah, that's exactly the problem. Laziness is the problem, yeah. Okay, so the talk is going to be about my joint work with my former graduate student who is a postdoc at McGill now, Keiichi Ayakawa, and it's about classifying group actions on hyperbolic spaces. Hello? Okay. And I think this talk perfectly fits the main theme of this workshop because it's about actions, and being mathematicians, we like to classify things, right? So I'll explain what that means. The idea is that for many groups admitting non-trivial in certain sense actions on hyperbolic spaces, it's not enough to look at just one action to recover all the feature of the group. And so the natural question is how we can describe all these actions. And there are two different approaches. One was taken in our joint paper with Sahana Balasubramania, who is here, and Caroline Abbott, who is not here, a few years ago, where we introduced the partially ordered set of group actions on hyperbolic spaces. This talk is going to be about a different approach where we consider a Borel space, and we can analyze the complexity of this space using descriptive set theory. Okay, so I guess everybody knows that, but I'll repeat. If you have a group acting by isometries on a hyperbolic space, and whenever I'm talking about groups acting on metric spaces today, I always assume that the actions are by isometries by default. An element is called loxodromic if it has the so-called north-south dynamics. So there are two fixed points on the boundary of the Gromov hyperbolic space, so that one point serves as an attracting point, means that if you start iterating your element G, then the orbit of every point except for G minus will converge to G plus and vice versa. And an action of a group on a hyperbolic space is said to be of general type if there are two transversal loxodromic elements. Transversal means that their fixed points on the boundary are totally disjoint. Okay. And this is somewhat minimal requirement which you need to extract some useful information from the existence of such an action, because like the basic thing you can extract from the existence of a group action on a hyperbolic space is the existence of non-cyclic free subgroups, right? And that's the classical ping-pong argument. But to play ping-pong, you need exactly two transversal loxodromic elements, right? So that's sort of the minimal requirement. And well, for the action to be useful, and I'll call a group weakly hyperbolic if it admits a general type action on a hyperbolic space. There are no assumptions about properness of the space, properness of the action, co-boundedness of the action, just any general type action on a hyperbolic space. And here are some examples of groups which are weakly hyperbolic. So of course every non-elementary, meaning non-virtually cyclic, hyperbolic groups, or more generally every cylindrically hyperbolic group is weakly hyperbolic. But the class of weakly hyperbolic groups is not limited to that, so there are other groups, say bounce-like solitary groups, which are very far from being a cylindrically hyperbolic or relatively hyperbolic or whatever you want. But they are weakly hyperbolic because the corresponding action on the bus cert tree satisfies the definition. There are two transversal loxodromic elements, provided these numbers m and n are not equal to 1 in the absolute value. And also, if you take any subring of complex numbers and consider the group SL2R, it's going to be weakly hyperbolic, well, just because it acts on H2 or H3, hyperbolic two-dimensional, three-dimensional space, depending on whether R contains complex numbers or not. And the action is going to be non-elementary because already the action of SL2Z in both cases is, of general type. Yeah. Okay, and the problem I'm going to talk about today is, given a group G, classify all general type G actions on hyperbolic spaces. By hyperbolic spaces, I mean Gromov hyperbolic spaces, not necessarily Hn. And of course, I have to explain what it means to classify. So when we talk about a classification problem, first of all, we implicitly assume that there is some sort of an equivalence. And also, I'm going to talk about the complexity of this problem, and that also requires some background. So before talking about the necessary background, I want to give you two examples, like motivating examples, which show two groups, and one has classifiable actions on hyperbolic spaces. I'm talking about general type actions, and the other is not of that type. So the first group, SL2 over Z adjoint square root of 2. Yeah. So if you take, if you consider this group, there are two embeddings of something is wrong. I'm sorry. Something is wrong with my computer. Okay, now it wants to install the update. Very sorry about that. Hope it will take a minute. Yeah, that's why I never use slides. You always run into this kind of problems. Okay, let's see. Somewhat different.
You can send me your slides and give me my laptop.
Yeah, I don't have access to the internet. That's the problem. Okay, let's see. I may be able to. Yeah, it works. Okay, so now I think. Okay, so here we are. I'm sorry about that. Okay, so going back to my example, there are two embeddings of SL2Z adjoint square root of 2 into SL2R. And one is the straightforward embedding, the other is twisted by the non-trivial element of the Galois group. Okay? So each of these two embeddings gives you an action on the hyperbolic plane, and it's a non-trivial result, which is a consequence of a more general theorem proved by these four authors, that every action of SL2Z over square root of 2 is essentially one of these two. Essentially one of these two means that if you have any action of this group on a hyperbolic space, any hyperbolic space, not necessarily H2, then you will see a quasi-isometrically embedded copy of H2 inside your space, which is coarsely equivariant under this action. And when you restrict the action to that copy, then you see one of these two actions described above. So this is a perfect example where the set of all actions of a group on a hyperbolic space, well, can be described. And on the other side of the spectrum, we have the free group on infinitely many generators, or you can even take F2. And of course, if you have any countable group acting on a hyperbolic space, there is an action of the free group, F infinity, that factors through that action. So asking to classify all actions of F infinity on hyperbolic spaces is the same as asking to classify all possible actions of all possible groups on hyperbolic spaces, which is clearly a wild problem. Okay? So you see that in the first case, actions are kind of classifiable. The second case, they are not classifiable. Now I want to explain the precise meaning of the word classifiable. And for that, I will need some preliminary background from descriptive set theory. So the ideas I'm going to quickly describe, they come from operator algebras and ergodic theory, and the contemporary theory has significant input from logic. So the idea is to formalize a classification problem as a pair, X and then some relation on X, where X is a topological space. And at first, forget about the topological structure on X. So what is a classification problem in mathematics? You have some set of objects, you want to classify them up to certain equivalence, right? And that's the classification problem. Now, the topological structure on X allows you to analyze the complexity of the classification problem. And I'll explain this in more detail in on my next slide. So let me show you how you can formalize some familiar classification problems in this way. So suppose you want to classify countable graphs up to the isomorphism relation. What is a countable graph? The set of vertices can be identified with natural numbers, right? And then a countable graph on natural numbers is simply a subset of n cross n. So let's talk about symmetric subsets because we want undirected graphs. And each subset like this tells you where, the edges are, right? So you can identify the set of all countable graphs with the collection of all symmetric subsets of n cross n. And this sits in the set of all subsets of n cross n, which has a natural topology, the product topology, with respect to which it's a counter set. So you restrict this topology to this subset and you get your topological space. So that's the topological space of countable graphs. And the equivalence relation is induced by the isomorphism relation. Two subsets E1, E2 of n cross n are equivalent if the corresponding graphs are isomorphic. So this is nothing else but the orbit equivalence relation of the symmetric group acting on natural numbers. And that's an example of a formalization of a familiar classification problem in this way. Okay? Now, as I said, the topological structure on X can be used to compare a complexity of two different classification problems. So suppose we have two classification problems here, X and Y are topological spaces, E and F are certain equivalence relations. We say that, well, informally we want to say that the first classification problem is not harder than the second if you can explicitly reduce the first problem to the second. Meaning that if you can classify elements of Y up to the equivalence relation F, then you can somehow classify elements of X up to the equivalence E. So Y serves as the set of invariants which provide you with the classification. And this reduction, the computation of invariants, must be explicit. Now, what does it mean to be explicit? Well, there is this informal statement, which is sometimes called Church thesis for analysis, that explicit means Borel. And the reason is that, of course, to construct something non-Borel, you usually have to use the axiom of choice. So here is the classical definition, which goes back to Friedman and Stanley. Suppose, okay, so we say that the classification problem XE is Borel reducible to the classification problem YF. If the following holds, there exists a Borel map from X to Y such that two elements of X and B are E equivalent if and only if their images are F equivalent. Okay? And then we consider the equivalence relation induced by this quasi-order. So XE is Borel bireducible with YF if and only if they are Borel reducible in both ways. So here are some examples. Suppose you have Polish spaces X and Y, and the most basic classification problem is classification up to the equality relation, which is trivial, right? 2 points are equivalent if and only if they're equal. So the classification problem on X up to equality is Borel reducible to the classification problem on Y up to the same, up to equality, if and only if the cardinality of X is less than or equal to the cardinality of Y. So why is that? Well, in one direction it's trivial, because if your equivalence relation is equality, this condition explicitly tells you that the map must be injective, right? And since the map is injective, the cardinality of X must be less than or equal than the cardinality of Y. In the opposite direction, you have to use the classification of Polish spaces up to Borel isomorphism, which says that up to Borel isomorphism, every Polish space is either a finite space or countably infinite discrete space, or the interval 0, 1, or real numbers, whatever you want. This classification immediately gives you the other implication. Okay. So now we are going to talk about Borel equivalence relations on topological spaces, and an equivalence relation on a topological space is called Borel if it's Borel as a subset of this set cross itself. And now there is a class of Borel equivalence relations which serves as an initial segment of the complexity hierarchy. So these relations are called smooth, and these are precisely the relations that are reducible, Borel reducible to the equality relations on Polish spaces. So what that means that sometimes the corresponding classification problems are called concretely classifiable. Well, why is that? Because essentially this definition says that if you have a classification problem, you can explicitly assign some invariant from a Polish space which tells you when two objects are equivalent. So they are classifiable by explicitly computable invariants from which are points of a certain space. Okay, and here is the description of all possible smooth Borel equivalence relations up to Borel bireducibility. So up to Borel bireducibility, every smooth Borel equivalence relation is either the equality relation on a discrete space, or the equality relation on the discrete finite space, or discrete countable space, or real numbers. You can also replace real numbers with the interval 0, 1. So this is a corollary of the Kuratowski theorem, which is the classification of Polish spaces up to Borel equivalence, Borel isomorphism, plus another result which is known as silver dichotomy. So anyway, these are all possible smooth Borel equivalence relations, and there are of course many Borel equivalence relations that are not smooth. If you have any group acting on a Polish space by homeomorphisms, and if your group has a dense orbit, the corresponding induced orbit equivalence relation is going to be non-smooth. Well, if your Polish space is perfect, let's say this. If your Polish space has no isolated points. A particular example of this is the familiar Vitali relation, which is the orbit equivalence relation of the standard action of Q on R. The fact that this is not smooth is a very easy consequence of the Bayer category theorem. So it's, you can think of this as an exercise. The proof is just a few lines. And there is another non-smooth equivalence relation, which is a little bit more difficult to define, but it will play an important role in my talk, so I'll define it here. That's EL infinity, and this is essentially the equivalence relation induced by the action of L infinity on R to the power n, the set of all sequences of real numbers. So L infinity acts on this set of sequences just by addition. And this is the equivalence, the orbit equivalence relation generated by these actions. So two sequences are equivalent if and only if the supremum between the corresponding entries of these sequences is finite. So here is the picture that illustrates the hierarchy, the complexity hierarchy of Borel equivalence relations up to Borel bireducibility. So as I said at the very beginning, you have this initial segment consisting of smooth Borel equivalence relations. And then the next step in the hierarchy is the orbit equivalence relation of Q over R. And this is indeed the initial segment, meaning that if you have any Borel equivalence relation, it will be either one of these or it will be strictly greater than all of them. So that's like the full initial segment. So then my picture becomes incomplete because there are lots of things on the sides which may not be comparable to what's on the picture. So it's just some small part of the world of Borel equivalence relations. You have a continuum of Borel equivalence relations with countable equivalence classes, and the structure they form, the partially ordered set up to Borel reducibility, is very complicated. So it's a huge set here, and then this set has a maximal element, and this maximal element is the action of the free group on two generators or any other finite number of generators greater than 1 on the set of all subsets of F2. It should be F2, not F squared. It's a typo. So all these relations are Borel, and EL infinity is here. It's also a Borel equivalence relation. There are some non-Borel relations. Some of them I have already mentioned, specifically the isomorphism of countable graphs. This equivalence relation is not Borel. It's the so-called analytic. And if you have any other classification problem, which is reducible to the isomorphism problem of countable graphs, that classification problem is said to be classifiable by countable structures. Or you can say classifiable by countable graphs, but it turns out that if you replace graphs with arbitrary algebraic structures in the model theory sense, in arbitrary countable signature, you don't get anything else. So whatever is classifiable by countable structures can also be classified by countable graphs. And that's not very difficult. And then, as I mentioned, this is essentially an orbit equivalence relation of the action of the symmetric group on natural numbers. So you can more generally consider actions of Polish groups on Polish spaces, and that gives you a huge set of equivalence relations induced by these actions. In general, they are not analytic, they are Borel, and this set also has a maximal element. Okay? So why am I mentioning this? Well, what you have to take from this picture is that this EL infinity, which I'll use later in my talk, first of all, it cannot be, well, first of all, the corresponding classification problem is not classifiable by countable structure, so it's extremely unclassifiable in a certain sense. And second, this equivalence relation cannot be induced by any action of a Polish group. by any action of a Polish group on Polish spaces by Borel transformations. Okay. So that was some background from descriptive set theory, and now if you want to formalize the classification problem I mentioned in this setting, we need to define a topological space corresponding to group actions on hyperbolic spaces. And that can be done in general settings, but for the purpose of my talk, I want to restrict to co-bounded actions, which by the familiar Schwarz-Milner argument, well, is the same as considering just generating sets of your group. And this allows me to state some definitions in a simpler way. So I'll stick with this particular case. The general case is not very different. Essentially, you will see the same results in the general case. Okay, so suppose we have a group G, and so I consider the set of all generators of the group, which are organized in a topological space. Now, what's the topology? Well, the set of all generating subsets is the subset of the set of all subsets. And the set of all subsets has their product topology, or if you want, the topology of pointwise convergence of the indicator functions. So that's a Cantor set if the group is countably infinite. So this is some subset of the Cantor set which inherits the topology. Now, what's the equivalence relation here? Okay, so we compare two generating sets according, roughly speaking, to the amount of information the corresponding calligraphs provide about the group. So what is the least useful calligraph of your group? Well, you take all elements of your group as generators. Then the calligraph is just the complete graph where there is an edge between any two vertices, right? What can you say about the group by looking at this graph? Well, perhaps you can say it's infinite and that's it, right? Nothing. All the information is lost. So this is going to be the minimal element in our order. And then if you have a finitely generated group, the calligraph with respect to a finite generating set usually keeps as much information as you can extract from geometric arguments, right? So that's going to be the largest element with respect to our order. Okay, so now the formal definition is this. We say that the generating set Y dominates X if the identity map between the corresponding metric spaces, or if you want, you can think of this as the map between calligraphs, which is defined on vertices, not necessarily edges, is Lipschitz. So meaning that like the calligraph with respect to Y is sort of larger than the calligraph with respect to X, and the calligraph with respect to X is obtained by contracting things, right? Okay. So, of course, we consider the equivalence relation induced by this quasi-order. And here are the examples which I've already mentioned. If you take X to be the set of all elements of G, then this generating set is dominated by any other generating set, because the corresponding metric space here will be bounded, right, of diameter 1. And if you have a finite generating set for your group, it will be the maximal, the largest actually element in the corresponding partially ordered set. In particular, all finite generating sets are equivalent, so they form a unique equivalence class. And here is an example of two generating sets of the group Z plus Z, which cannot be compared, so they are incomparable. The first generating set, you take 1, 0, and then take the whole second multiple, or second summand here, as the set of generators. And the other generating set is sort of symmetric. You take the first summand here and add one generator of the second summand. And of course, these two generating sets are incomparable because there are sequences of elements which have bounded size in one generating set and growing size in the other generating set. Okay? So you cannot compare these two sets, generating sets in any way. So this generating sets of, for a general group, these generating sets form a very complicated partially ordered set. Now we are not particularly interested in that big partially ordered set. We want to consider generating sets corresponding to co-bounded actions on hyperbolic spaces. And these are, okay, so first we consider the set of all hyperbolic generators of G, which is the set of all generating sets such that the corresponding Kelly graph is hyperbolic. Okay. And among these, we consider this generating sets for which the action of the group G on the hyperbolic Kelly graph is of general type, meaning that it has two transversal loxodromic elements. Okay? And again, I want to stress that we consider these sets as subsets of this Cantor set, so they inherit some topological structure. And if you wonder whether what is the topology behind these sets and the equivalence relation we just introduced, here is a result which is not very difficult. So the space of all generating sets of a group, if G is countable, is a Polish space, meaning it's completely metrizable, separable, completely metrizable space. The equivalence relation we introduced is a Borel equivalence relation on that space. And these two subsets are Borel subsets of the space of generating sets. So everything is kind of Borel or explicit, whatever. So this is, yeah.
This is a very nice question. I mean, can you relate this solution of classification with any kind of more geometric sounding classification between actions on hyperbolic spaces?
You mean the equivalence relation, which? Yeah, well, in the general situation, if you have two actions, we say that they're equivalent if there is two actions of a group G. We say that two actions are equivalent if there is a coarsely equivariant quasi-isometry from quasi-isometric embedding from one space to the other space and vice versa. So if you see one action inside the other and the other action inside the first one. And when you restrict to co-bounded actions, it is essentially what I defined. And here is the main theorem which we proved. So it turns out that for any countable weakly hyperbolic group, and remember weakly hyperbolic means that it has an action on a hyperbolic space with two transverse loxodromic elements. For any countable weakly hyperbolic group, the classification problem we are interested in, meaning the classification of general type hyperbolic generating sets of G with respect to this equivalence relation I just introduced, is Borel bireducible to one of these relations, either a smooth relation or EL infinity, and all possibilities realized. Now, if you want the corresponding result for actions of groups on hyperbolic spaces, it will be exactly the same. So actions, group actions on hyperbolic spaces can be organized in a topological space in a similar way, and then with respect to the equivalence relation which I just described, the result will be precisely the same. And what's interesting is that all possibilities realize. Okay, so here is the graphical representation of our theorem, which shows which levels of this complexity hierarchy can be realized. So you have the first initial segment up to the equality on real numbers, and then you have this EL infinity. So this is sort of surprising because the groups which produce equivalence relations here, they still have lots of actions, lots of non-equivalent actions on hyperbolic spaces, but somehow those actions are easily classifiable. So from the point of view of geometric group theory, the interesting thing is that you have this very nice class of hyperbolic groups, and I want them to be non-elementary, so let's say non-elementary. I'll abbreviate non-elementary hyperbolic groups. And then there are larger classes which have similar property, for example, the class of acylindrically hyperbolic groups. And then there is this big class of weakly hyperbolic groups. Now, the thing is that the class of weakly hyperbolic groups can be divided into two subsets. And groups in the first subset, they are somehow close to being acylindrically hyperbolic. In what sense? Well, these groups, hyperbolic, acylindrically hyperbolic, they admit a lot of quotients. They are never simple. So groups in this class, they are sort of the same, they feature sort of the same flexibility in the sense that, well, these groups actually can be simple, but their actions on hyperbolic spaces can be modified in so many ways, and they have a huge hierarchy, huge and very complicated sets of actions on hyperbolic spaces, while groups here are sort of very rigid. So their actions on hyperbolic spaces can be described by precise invariance, and I'll mention this in a second. So in the remaining 20 minutes, I'm going to talk a little bit about the proof of the theorem, and I think the proof is interesting by itself because it tells you how to distinguish between the groups here and here. Okay, so I'll start with a definition which makes sense for any space, not necessarily hyperbolic. If you have a group.
Excuse me, Denis, could you give some examples? Okay, so okay, you have this basically complete list, right? Can you give? I assume that SL2Q square root of 2 will be of this, whatever this is called, yeah, out there.
Yeah, even SL2,
right.
SL2Z adjoint square root of 2 is here. Yeah.
Oh, right.
Yeah, and I'll give more examples. There will be more examples on my next to the last slide. Okay? Yeah, you will see more examples. So let's talk about this definition. We say that an action of a group on a metric space is isotropic if there exists a constant, which I sometimes will call isotropic constant, such that for every 2 points, A, B, A prime, B prime in my metric space, which are equidistant, meaning the distance between A and B is the same as the distance between A prime and B prime, there exists an element of my group that maps the first pair close to the second pair, meaning that the distance between GB and B prime is at most D, and GA and A prime is at most D. Okay? Now, the intuition is this. You think about these pairs of points as directions in your space. And roughly speaking, what this definition tells you, it tells you that all the directions in your space are more or less the same modulo G action, right? So that's why we call these actions isotropic. Here are some examples. So the action of Z on R is very close to being isotropic, but it's not isotropic because you cannot reverse the orientation, right? Now, if you consider the action of the dihedral group, which has this involution that reverses the orientation, well, this one is isotropic. And when it comes to hyperbolic spaces, it turns out that you can determine whether the action of your group on a hyperbolic space is isotropic just by looking at the dynamics of the induced action on the boundary. Specifically, for any general type action of a group G on a hyperbolic space, the action is isotropic if and only if it's co-bounded, and the induced action on the pairs of distinct points on the boundary is minimal in the topological sense. Minimal in the topological sense means that every orbit is dense. Okay? So immediately from this description, you can see that the action of SL2Q on H squared is isotropic? Well, because the action is, well, every orbit on the boundary is dense, and the action of SL2Z on H2 is not isotropic. Okay. Now, more generally, if you have a proper action on an unbounded hyperbolic space, that action is not going to be isotropic because you will never have dense orbits on the boundary. Okay. Now, a weakly hyperbolic group is called isotropic if for every generating set from this set, remember this is the set of all generating set such that the corresponding Kelly graph is hyperbolic and the action of G on that Kelly graph is of general type. The natural action of the group on the Kelly graph is isotropic. Okay? So here, well, and we say that our group is anisotropic if it's not isotropic. And here are some examples of anisotropic examples. For example, all non-elementary hyperbolic groups are anisotropic. H&N extensions with proper associated subgroups, for example, these Baum-Slack solitary groups are always anisotropic. And here is a proposition which allows us to provide examples of isotropic weakly hyperbolic groups. So the proposition says that a weakly hyperbolic group which is uniformly perfect or boundedly generated is always isotropic. Remember, uniformly perfect means that there exists number n such that every element of your group is a product of at most n commutators. Okay? So here are some familiar examples. If you take SL2F for any subfield of C, this group is boundedly generated. What am I saying? It's not boundedly generated. It's uniformly perfect. It cannot be boundedly generated because it's not even finitely generated. But it's uniformly perfect and therefore isotropic. Here is another example which uses bounded generation. If R is any ring of algebraic numbers, then either this group SL2R is isotropic or R is contained in the ring of integers of an imaginary quadratic field. And these two possibilities are mutually exclusive. Okay. So for example, SL2 Z adjoint square root of 2 is anisotropic because 2 is not negative. Okay. Now, for isotropic groups, we have an interesting phenomenon which we call translation length rigidity. And before talking about our result, I want to remind you this result by Alperin Bass and independently by Kuller and Morgan, which was proved a long time ago. So, for any group acting on a metric space, you can define the translation lengths of an element in the usual way. So that's the infimum, sometimes called the displacement function. And it turns out that if you have two minimal general type actions of a group on two R trees, here the word minimal is used in the sense of the action on trees. So there is no proper invariant subtree. So two minimal general type actions of a group on two R trees induce the same translation length function if and only if they are equivariantly isometric. So if you want to classify actions on R trees up to equivariant isometry, the translation function defined this way provides you a complete invariant. Interesting. So in our situation, the equivalence relation is slightly different. So we want to classify our generating sets or the corresponding actions on Kelly graphs up to a slightly weaker, well, considerably weaker equivalence relation. But we still have a similar theorem. Instead of the translation function defined here, we consider the translation function, the stable translation function defined in this way. So you take any generating set of the group and you take the lengths of G to the n, the nth power of your element, with respect to the generating set X, and then divide by n. The limit always exists. It's a well-known fact, and we denote this by tau sub x of g. And then we consider all multiples, the equivalence class of this translation function, translation length function, with respect to scalar multiplication. So essentially, this is a point in the projective space of r to the power g. And it turns out that we have a similar rigidity phenomenon. So suppose we have an isotropic weakly hyperbolic group. That's important, that the group is isotropic. Then for any two generating sets from this set, so that the corresponding calligraphs are hyperbolic of general type, we have the length functions are proportional if and only if the corresponding generating sets are equivalent in the sense which I described before.
So is this the prerogative result about being 1A plus isometric translation?
Yeah, you have a similar result for actions, if that what you mean. Yes, there is I mean, in our paper, the same result is stated for actions, and this is just a corollary. Yeah. And in one way, it's non-trivial in both ways. Even if you know that two actions like X and Y are equivalent, how do you know that the translation, you know that translation length functions, one is bounded by a multiple of the other and vice versa. But this is much stronger. This says that one is exactly equal to a scalar multiple of the other, which is a considerably stronger property.
And presumably there are counterexamples if you remove isotropic.
Yes, there are counterexamples if you remove whatever you want. If you remove isotropic, there are counterexamples. If you remove GT condition here, if you are willing to consider, say, non-elementary actions instead of general type actions, there are counterexamples, and well, yeah. This is, no, no, it's not time for that. Okay, cool. Good. So, where did I go? Okay, so now I'm ready to present the proof of my theorem, and just, well, our theorem. And just to remind you, here is the theorem, that for every weakly hyperbolic group, the classification problem we are concerned with is Borel bireducible to one of these classification problems which I described earlier, and all possibilities realized. And of course, there are two cases. So if G is an isotropic group, then it's not difficult to show that this projective space of invariance is Polish, and the map from this hyperbolic generating sets of general type to this projective space that assigns to every generating set the corresponding translation function on G is Borel. So it serves as a Borel reduction, and therefore it's a smooth equivalence relation because the translation length function, or rather its equivalence class with respect to scalar multiplication, so which is the equality relation on this Polish space, serves as a complete invariant for our classification problem. So this is done. Now, what if the group is anisotropic? Well, this situation is more complicated. And it turns out that if my group is anisotropic, first of all, what I know that there is one general type calligraph for which the action of the group on this calligraph is anisotropic. Then it turns out that we can find infinitely many directions which are independent with respect to the G action. And we can equivariantly compress our action in those directions, and this can be done independently, which gives you an embedding of this relation EL infinity into the classification problem we want to solve. So this is a little technical and requires some sort of small cancellation type arguments, but that can be done. And so for anisotropic groups, we get the complexity level of our classification problem is exactly EL infinity. Well, Okay, so we get just one inequality, but that inequality is elementary. So it's actually EL infinity up to Borel by reducibility. Now this is the outline of the proof. I also claim that all possibilities realize, and here comes the slide with examples, which shows in particular that all possibilities indeed realize. Okay, so first of all, I want to remind one result which we proved in our paper with Sahana and Caroline. There exists a group, we call it I, such that up to equivalence, this group has only one general type action on hyperbolic spaces. So in our notation, the set of general type hyperbolic spaces, general type hyperbolic generating sets has exactly one equivalence class. Okay? Now, if you take the nth direct power of this group, you will get a group that realizes the equivalence relation, which is equality on the set with n elements for the corresponding classification problem.
Sorry, Dennis, is it easy to define this group I?
No, in our paper, it's defined as a group with certain prescribed local actions on a tree, and that's no, that's a little technical, and it uses some non-trivial results by other people. So yeah, that's non-trivial. But there are some easy examples. For instance, if you take an irreducible lattice, and this is a consequence of a theorem proved by Butter, Furman, Sista, and Capras, right? If you take an irreducible lattice in SL2R to the power n, where n is at least 2, then you will have a group which realizes exactly this complexity level, like the group SL2 over Z adjoint square root of 2, which corresponds to the case n equals 2, right?
It doesn't cover all the Hilbert modular groups.
Hmm?
It doesn't cover all the Hilbert modular groups. So if your ring of integers has some complex.
Well, no, because if you take Z adjoint square root of -2, that one is acylindrically hyperbolic, so it belongs to a completely different world. It's here. So now, what if you want a group which has countably many, infinitely many actions on hyperbolic space up to equivalence? Well, you can take any group from the first cell here and take well, a countable direct sum of copies of this group, and that will be an example. I also conjecture that the group of rational numbers belongs to this, that the group of rational numbers belongs here, but at this time, we don't have the proof. And if you want to have a group which has a continuum of actions on, well, general type actions in hyperbolic spaces, which are nevertheless classifiable, then you can take SL2 over every countable transcendental extension of Q. For example, SL2 over Q of X, the field of rational functions. Okay. Now, for anisotropic examples which realize EL infinity complexity, you can take any non-elementary hyperbolic group, or more generally, any acylindrically hyperbolic group, or even more generally, any group which is not virtually abelian and contains a WWPD element. If you don't know what is that, just ignore. But anyway, any non-elementary hyperbolic or acylindrically hyperbolic group would work. Or you can also consider Baum's-Lax solitary groups, which are very far from being hyperbolic or acylindrically hyperbolic. They also realize the same level of complexity of the classification problem. Okay? And finally, that's my last slide, I want to consider I want to discuss an application to the partially ordered set of hyperbolic structures. At the very beginning of my talk, I told you that there is another approach. Instead of considering this, doing these Borel considerations, you can consider the partially ordered set of the so-called hyperbolic structures. And, well, I just want to remind you that's the definition of the partial order on generating sets, which we discussed earlier. Now, if you take all hyperbolic general type generating sets of G and mod out by the equivalence relation, you get a partially ordered set, which is equipped with a real partial order. So this is a quasi-order. When you mod out by the induced equivalence relation, you get a partial order. And this is a partially ordered set, which is called the poset of general type hyperbolic structures on the group G. Now, when we wrote our paper with Caroline and Sahana, we provided some examples of groups for which this set can be computed. And interestingly, in all examples in our paper, this poset is either very simple or very difficult to describe, kind of undescribable. And it turns out that this is not a mere coincidence. Actually, from our results, it follows that there is a dichotomy which states precisely that for every countable group. Namely, for every countable weakly hyperbolic group G, exactly one of the following conditions holds. Either this partially ordered set of hyperbolic structures is an anti-chain of cardinality anything from 1 to aleph 0 or perhaps continuum, and all possibilities can be realized. So this is the simple case, it's an anti-chain. Or it contains every partially ordered set of cardinality at most aleph 0, which means it's very complicated, right? Unlike in the first case. In particular, if you want to accept the continuum hypothesis, then this is a universal poset of cardinality continuum, meaning that it contains any other partially ordered set of the cardinality of the continuum. So it's a very complicated poset. So indeed, this dichotomy at the level of the poset of hyperbolic structures holds not just for the examples in our paper, but in fact for any countable group. Okay, and that's it. I want to finish here.
Are there any questions?
What about the complexity of actions of lattices and Lie groups?
Complexity of
actions of lattices and Lie groups.
Well, if you have a lattice in a Lie group, under suitable assumptions, all actions on hyperbolic spaces will come from projections to rank 1 factors. And so you have the theorem which I mentioned. If you have a lattice in a product of rank 1, simple rank 1 Lie groups, then the complexity is, well, it's equality on the number of factors. That's the theorem by Fuhrman, Butter, Capras, and Sista. So yeah, essentially there is nothing crazy coming, nothing interesting coming from this world.
And so
Denis? Oh, sorry.
Yes.
Denis, in the last corollary, is it again dichotomy isotropic versus non-isotropic?
Yes.
Isotropic the
yes.
first case and non-isotropic the second.
Yes, exactly. That's exactly the case. Yes.
So in the previous slide with all the examples, in the case of equality of n and equality of r, do you have finally generated examples?
No, we don't have. Oops, we don't have any finitely generated examples here or here. So it would be nice to have some.
Just want to ask a very small question. So in the last slide, and so yeah, in the very last corollary, and in part B, you say contains every poset of cardinality So you roll at most Aleph 1, but you say, I think you say at most Aleph 0. Is it Aleph 0 or Aleph 1?
No, it's Aleph 1.
Aleph 1, okay.
Aleph 1. Oh, did I say Aleph 0? No, Aleph 1. That's why if you assume the continuum hypothesis, you get a universal poset.
Fantastic.